So let's do the molecular orbital diagram for methane. So as always, we're going to identify the point group. I think you know this off the top of your head that this is tetrahedral TD. Next, we're going to make salts of the pendant atoms. So the pendant atoms, again, are the non-central atom ones. Those are going to be methane, and those are going to be hydrogen, sorry. And because we only have hydrogen as our ligands, hydrogen only has 1s orbitals available for bonding, just like the example we did before with beryllium hydride. And so we're going to represent sigma bonding as vectors pointed towards the central atom, kind of representing electron density that's going to be going towards making these bonds from these salts or these hydrogens. Okay. So once we have this picture, we can define our coordinates. I'm going to define the z as going straight up here. That's going to be, you always have to define it as being the principal rotation axis. There's the principal rotation axis here is a C3. There's many different C3s. There's 8 of them, in fact, in methane. So you have a lot of options. I just chose the one that's pointing up. All right, so then what we're going to do is we are going to come up with a representation for these salts. And so to do that, we have to apply the different operations and see how these vectors that represent sigma bonding transform, right? And so, remember where this all comes from is you're essentially doing a matrix here. You're asking what matrix takes V1, V2, V3, and V4. And for identity, we know that it's just V1 goes to V1, V2 goes to V2, V3 goes to V3, and V4 goes to V4. That's what I have written here. And we're going to have ones across the board and zeros everywhere else, right? And so the character of this matrix is going to be the sum of the values along its main diagonal. So the character is going to be 1 plus 1 plus 1 plus 1, which is equal to 4. So we put down a 4. We carry on, and now I'm not going to write the matrices anymore. Basically, if anything goes in itself, you're going to get a 1 on the diagonal. If something goes to something else, you're going to get a 0 on the diagonal. If it goes to the negative of itself, you're going to get a -1 in the diagonal there, right? So you can think about a C3. A C3 is going to give you a V1 is going to go into V1. But then V2, V3, and V4 are all going to interchange, right? It's like spinning a tripod. And so in that way, you're going to get a character of 1 because your matrix is going to, again, just to be very clear, is going to have something like this along the diagonal. And we don't care about what these off-diagonal elements are, but we're going to have that. And again, this is V1, V2, V3, and V4. So we're summing up along here. That gets us a 1. Next is going to be a C2. The C2 runs, it's a little harder to visualize, but runs something like that. And so this H goes to this H and vice versa. And these H's go to one another. That's one example of one of the C2s. There's 3 of them. But that causes V1 to go to V2 and vice versa, and V4 to go to V3 and vice versa. So all of them interchain, all the vectors interchange, so we're going to get 0 there. S4 is in the same axes as the C2. So that's going to be right there. Remember, that's a 90-degree rotation of C4, so it's going to kind of go out into space here. But then that's going to get flipped and go to the other side and be one of these hydrogens. So anyway, all of those vectors are going to end up getting changed. And because of that, you're going to have zeros along the diagonal, and you're going to get a character of 0. Last one is sigma D. There's 6 sigma Ds in the molecule. You can choose whichever one you want. I'm choosing the one that's easiest to draw, which is right here. Okay, and so it's in the plane of this hydrogen-carbon-hydrogen bond. Because these vectors, V1 and V2, are in that plane, they're not going to move. So V1 goes to V1, V2 goes to V2. but then these hydrogens are flipping places. So these vectors, V3 and V4, are also going to exchange places here. So two of them stayed the same. So I had, 1, 1, 0, 0 in my matrix here. And so the matrix would look something like this, right? And of course, if we take the trace of that matrix, we're going to 1 plus 1 plus 1 plus 1 plus 0 plus 0 is 2. Okay, so that's our reducible representation for our salts. Now we have to reduce that. If we reduce that using the formula that we went over in chapter 2 or by inspection, you'll see that this is A1 plus T2. Here are what the salts look like. You're always going to have a totally symmetric salt, and that's going to be all the orbitals just in phase. So we have s orbitals, we can write them all as light, or we can write them all as dark. Those are equivalent. And so that one's always easy to get. The T2 salts are harder to get. And so, it's harder to know, intuit, why do these three salts have T2 symmetry? Obviously, there's three of them because T Molecular symbol has a dimensionality 3, so it tells you 3 things transform together. In this case, it's 3 salts. But why does this have T2 symmetry? I'm going to go over that in the next video. But right now, we had 4 1s orbitals of hydrogen. We combined them in different ways. We did the representation, reduced that representation, and got out 4 different salts. So we started with 4 atomic orbitals, 1s orbitals on a hydrogen, and you ended up with 4. One of those is always going to be the totally symmetric one, the A1 salt, and then some other salts. In this case, you have 3 that are of T2 symmetry.